Here we have a graph of the function z equals x cubed plus y cubed minus 3x minus 3y. You can see that the axes are oriented a bit differently here from what you're used to seeing. The negative y-axis is along here actually, and the negative x-axis is along here. So positive x and y is back here. The origin is a point that's actually 4 units above this point. You can see z equals 0 here, so the origin is somewhere in here. Anyway, we are interested in stationary points of this function. Point A is an example of a stationary point. It's an example of a local maximum. The partial derivative of z with respect to y at this point A is actually 0. So the partial derivative of z with respect to y gives us the slope of a tangent to the surface at A, but a tangent in the y direction. Now we can call our function f instead of z, so you can write df dy for that partial derivative. So it's the slope of this line here. The x values of all the points on this line are the same. So are the z values actually. Only the y values change. Anyway, we can write df dy. We could also write dz dy. This partial derivative is worked out at the coordinates of the point A. Now let's consider this line here. This is a tangent at the point A, but it's entirely in the x direction. Its slope is the partial derivative of f with respect to x evaluated at A, and that will be 0. It's a horizontal line, its slope is 0. Okay, let's go and get these partial derivatives. Differentiate this thing with respect to y. So we treat x as if it's a constant. So x cubed becomes 0, y cubed becomes 3y squared. Minus 3x goes to 0, minus 3y becomes minus 3. Let's get df dx. So we pretend y is a constant. Differentiating x cubed with respect to x gives 3x squared. This term goes to 0, the next term becomes minus 3. The y term goes to 0. The next step is to set both of these partial derivatives equal to 0, because at a stationary point they're both 0, whether it's a local max or a local min, or as we'll see later, a saddle point. That's point C or point D. So at a stationary point both of these equations have to be satisfied. So we want the coordinates of a point that satisfies both of these simultaneously. So we solve between these equations. Actually x doesn't come into this one. If we solve it, we get y equals 1. Well, plus or minus 1. Y equals the square root of 1. So we have two possibilities for y. Over here we actually have two possibilities for x. So let's list the stationary points. So let's suppose x is plus 1. Then y can be either plus 1 or minus 1. So we could have 1, 1. We could have 1, minus 1. That's when x is plus 1. Now let's consider the case when x is minus 1. Again, we have two possibilities. We could have y equals 1, or when x is minus 1 we could have y equals minus 1. So we found 4 stationary points. The x, y values of each of these points satisfy both of these equations simultaneously. It appears from this diagram that the point A is the point with coordinates minus 1, minus 1. Well, these are the xy coordinates of the point A. If we want the z coordinate of the point A, we have to plug minus 1, minus 1 into this here, into the equation of the surface. So we get minus 1 cubed, which is minus 1, plus minus 1 cubed, another minus 1. Minus 3 times minus 1 is plus 3. Minus 3 times minus 1 is plus 3. So we get 6 minus 2 is 4. So it appears that the coordinates of A are minus 1, minus 1, 4. Okay, we could determine that from this graph, but later on we will see how to classify stationary points using a mathematical method. Anyway, let's look at points C and D. Let's look at point D. The slope of the surface at D in the y direction is actually 0. So the tangent to the surface at D in the y direction is horizontal. Its slope is 0. So like before, like getting the slope of this line here, we get df dy, but this time we evaluate it at D. If we evaluate it at this point here, we will get 0. Now it turns out that the slope of the graph at the point D in the x direction is also 0. You know, you could consider the cross section of planes with this surface. Like to get this line here, we can imagine a plane that is parallel to the YZ plane, and consider its cross section with the surface. We would see one of these curves here. We might see this curve here. This green curve is the intersection of the plane with the surface, and its local maximum is at D. Next, we could consider a vertical plane which is parallel to the XZ plane. So roughly it would look like this. Well, and this plane would contain this tangent here. This is a tangent to one of these curves here, maybe this one here. Well, this line here is meant to be a tangent to this purple curve, and this blue line here is meant to be a tangent to this green curve. Anyway, these two derivatives will be 0. Now this point, as the name suggests, or as the picture suggests I should say, is called a saddle point. This is probably a slightly better picture. The purple curve looks like it's running along here. It looks like D has coordinates 1, -1. This is the x value. X value is along here. X is 1, y is -1. Well, they're the xy coordinates. To get the coordinates of D, to get the z value of D, we have to plug 1 in for x and -1 in for y. So we get 1 cubed, -1 cubed is -1, -3 by 1 is -3, -3 by -1 is +3. Looks like we get 0. Yeah, that kind of matches this picture here. The 0 value for z is here. So this point is coordinates 1, -1, 0. Now C is another saddle point, and there appears to be a local minimum further in here. The local minimum appears to be this point here, point with coordinates x and y coordinates 1, 1. Okay, and then you just plug 1 in for x and 1 in for y to get the z value. I won't bother doing that. But as for C, C has coordinates -1, 1. X is -1. Y is +1.